Hello there, friends and students. This is part 2 of the lecture series on microelectronics. This involves a discussion of questions and answers involving diodes. We'll begin by describing what we call semiconductors. We say that a semiconductor has an electrical resistivity that is intermediate between those of good conductors and of good insulators. Small amount of impurity can have a marked effect on the conductivity of a semiconductors. Okay. Examples of a semiconductor is or those what we call rectifying diodes and transistors. Another example of a semiconductor material are the light emitting diodes or LED for short, and what we call integrated circuits or ICs. The process of mixing a semiconductor material with an impurity is what we call doping. So consider the element germanium, which is considered a typical semiconductor material because of its 4 valence electrons. Germanium belongs to the group 4 uh, type of elements as can be seen in the periodic table. All right. So normally materials like germanium does not easily conduct or is not a typical conductor. Okay, it can be made to conduct, however, by adding small quantities of impurities such as arsenic or gallium. And this process is, as we have said, okay, it's known as doping. This is the process used to make uh, materials like diodes and transistors. So, if we are going to use an impurity element such as gallium, okay, gallium has 3 valence electrons. It belongs to family 3. All right. So, uh, it is a kind of semiconductor known as p-type semiconductor. Okay. And in this type of semiconductor, current is described in terms of the motion of the holes. All right. These holes behave as though they were positive charges since they move towards the negative electrode. So as illustrated in this figure, letter A, gallium, which is an acceptor impurity or a p-type semiconductor material, has only 3 valence electrons. So it can borrow an electron from the neighboring atoms of germanium. All right. The resulting hole is free to move about the crystal. Since there is a vacancy of an electron, all right, and that vacancy of electron is what we call the hole. So it is just an apparent, all right, an apparent what we call charge similar to a positive charge. It's in fact a space where there is no electron occupying that space. Okay, so to further understand what a hole current is, let's consider this next or second illustration. There is such thing as a conduction band and a valence band, right? So energy band diagram, this is how we call it, for a p-type semiconductor at a low temperature. Since this type of um, semiconductor material has a very small amount of what we call energy gap between the valence band and the conduction band, amounting only to about 0.01 electron volt. So there is a big probability for the valence electron, all right, the valence electron to move into the acceptor level, all right, leaving behind what we call the hole or the space or vacancy of an electron. And that explains uh, the concept of what we call the hole current. What if the element germanium is doped with an impurity such as arsenic, all right? So in this diagram, the impurity arsenic, which has 5 valence electrons, when used as a doping material or impurity for germanium, okay, we notice that there is an extra electron, all right, that is not paired with the electron of germanium, all right. So we consider arsenic as a donor electron because of its extra electron that is not paired, okay, with another electron coming from the neighboring germanium atom, all right. So as again shown in this diagram, letter B, because of its very small energy gap, all right, uh, there is a high probability for that particular electron, all right, to move to what we call the conduction band, okay, all right, as shown here, all right. So again, it leaves behind a space that is vacant, which explains how we are able to also have that apparent vacancy of electron known as the hole. But in this case, since the impurity is a donor electron, we are talking about an n-type semiconductor, all right? In which case, electric current is carried by the motion of the negative charges, okay? The negative charges meaning the electrons themselves, just like in a typical ordinary conducting metal such as copper. So for our first question, which one of the following materials would be in an n-type semiconductor? Letter A, silicon doped with boron. B, germanium doped with boron. Letter C, silicon doped with phosphorus. Or letter D, germanium doped with gallium. Alright, the answer is letter C. Why? As shown in the periodic table of elements, phosphorus, all right, when used as impurity or impurity element, as seen in the periodic table, it has a valence number of 5 since it belongs to family 5A. So it's considered a donor electron. Okay. As such, the charge carriers are the electrons themselves. So when silicon is doped with phosphorus, the material becomes what we call an n-type semiconductor. Question number 2. Which one of the following statements best explains why semiconductors are used, for example, in transistors? Why are they doped? Alright, letter A. Doping makes the charge carriers mobile. Letter B. Doping changes the conductive properties of the semiconductors. Letter C. Doping converts the semiconducting material into a metallic material like copper. Letter D. Doping converts the semiconductors into zero resistance superconductors. So which among these four choices is the best answer? Right? Why semiconductor devices such as transistors are doped? So our answer, let's point out first that inasmuch as the band gaps between the valence and the conduction band is so small, okay, for most semiconductors, doping with small amounts of impurities, okay, results to a dramatic increase in the conductivity of the material, right? Which implies that our best answer for this question is in fact letter B. Doping changes the conductive properties of the semiconductors, right? Without the impurities, um, a semiconductor material, typically such as silicon or germanium, are not good conductors, right? Especially at room temperature. So, using an impurity, an n-type or a p-type impurity, okay, can increase their conductivity. All right. Letter A is not true. All right. The purpose of doping does not mean that the charge carriers become mobile. All right. Neither it is or neither is it letter C. Doping converts the semiconductor material into a metallic material like copper. That does not happen. All right. All right. And letter D. Doping converts the semiconductors into zero resistance superconductors. All right. The principle behind superconductors is uh, not quite related to doping. So it's really letter B, which is the best answer for this question. Before we move on to the next question, let's first talk about a semiconductor material or device known as diodes. So here is a schematic diagram of a diode. It consists of a p-type semiconductor material and an n-type semiconductor material joined, okay, side by side. All right. If this symbol, the red dot, represents electron, while the circle with no shade, okay, represents what we call a hole. So this is how we imagine these charge carriers are distributed, right? If they are not yet, if the diode is not yet connected to any power source, such as a battery, this is how we can imagine the charge carriers are distributed, all right? They are distributed at random, okay? For the p-type material, we say that the holes are equally distributed, spread out at random. Likewise, the electrons in the n-type are also distributed equally in all parts of the n-type material. There is a portion between the two semiconductor material, all right, which we call the p-n junction. So it's a region that separates the two uh, types, the p-type and the n-type. Now, when this diode, right, uh, is connected to a battery, such as what is shown in figure 1b, all right, the positive electrode, meaning the p-type, is connected to the negative terminal of the battery, while the negative electrode of the n-type material connected to the positive terminal battery. So there is now an electric field established, all right, across the diode. So what happens to the charge carriers such as the holes and the electrons? All right. So each charge carrier, meaning the holes, will be migrating, all right, to this end of the p-type material. They tend to accumulate on this side, while the electrons in the n-type material also migrate towards the right end of the diode, leaving behind what we call a region of depletion. All right, the p-n junction becomes depleted of the holes and uh, the electrons, right, referring to the moving electrons and the moving um, holes. All right, and this kind of connection, where the p-type material is connected to the negative terminal of the battery and the n-type connected to the positive terminal of the battery, is called a reverse bias. All right, since there is practically no charge carriers can be found at the region of depletion, it means that in a reverse bias connection, there is no net flow of charge in the whole circuit. All right, and the diode acts like a valve, right? It acts like a water valve that doesn't allow current, all right, or charges to move in just one direction. Okay. In short, there is no current in the whole circuit when the diode is connected in reverse bias, okay, relative to the terminals of the battery. So, to summarize, in this figure, letter B, the holes in the P region migrate to the left and the electrons in the N region migrate to the right. So in the middle, there is a layer which has no holes, no free electrons, so it becomes an insulator. No charges can flow. This is the depletion layer, all right? And a diode connected this way is said to be reverse bias. So you have to take note carefully. In a reverse bias, where there is no net current in the whole circuit, it is the p-type that is connected to the negative terminal, the battery, while the n-type material is connected to the positive terminal. Call it reverse bias. All right, so in this second diagram, as shown, uh, you will notice that the p-type semiconductor material is not connected directly to the positive terminal of the battery, while the n-type is connected directly to the negative terminal of the battery. All right. So in this case, since there is an electric field, all right, which causes the holes, okay, to move to the right and are able to actually cross what we call the p-n junction And similarly, the electrons in the n-type are able to also cross over, okay, to the p-type material. And that this ability of the p-n junction to allow the continuous movement of charge carriers is said to be what we call forward bias. This kind of diode connection is said to be forward bias. So in a forward bias, the P end is connected to the positive terminal of the battery, while the end is connected to the negative terminal. All right. As shown, there is now what we call a continuous flow of charges, meaning there is no current in just one direction, or we call it direct current. Okay, the electrons and holes flow across the junction, so there is current in the whole circuit. Okay, in this way, the diode conducts a current in only one direction. All right. A characteristic property of a p-n junction or semiconductor junction is that electric current can pass through it much more readily in one direction than in the other. Right? This is what we mean by forward bias. And one such use of a diode when connected in this manner, forward bias, is for what we call rectification. Rectification means converting an alternating current into a direct current. Alternating, in other words, the direction of uh, current, okay, reverses. All right. Half the cycle it is positive, and half of the cycle it is negative. We will show this process of rectification in our succeeding examples. Moving on now to our third question. Which of the following statements is true? Letter A. In a forward bias, the p-type semiconductor is connected to the negative terminal of the battery. Letter B. In a reverse bias, the n-type semiconductor is connected to the negative terminal of the battery. Letter C. Both the p-type and the n-type semiconductors must be connected in reverse bias. And letter D. No current flows in a reverse bias connection. Alright, so which do you think is the best answer? It is letter D. No current flows in a reverse bias connection. Letter A is incorrect because in a forward bias, the p-type semiconductor is connected not to the negative terminal, alright, but to the positive terminal. So that's what makes this statement incorrect. And in letter B, likewise, in a reverse bias, the n-type semiconductor is connected not to the negative terminal, but to the positive terminal. Alright? Of course, letter C is also incorrect. For our question number 4, give the direction of conventional current if the terminal B in our circuit diagram is positive. Use the given letters and note that the arrow in the symbol of a diode points from positive to the negative. Okay, so this is what we call the symbol of a diode. The arrow points or is directed from positive to the negative. Alright, that's the meaning of the arrow, positive to negative. So in the circuit, you have here a power source that is an AC voltage or alternating current voltage. That symbol there represents a sinusoidal wave representing alternating current. So at point A, and this is point B, notice that there are 4 diodes connected as shown. Alright, so each point here, for example, is point D, that is point C, that's point E there, and this is point F. There is a resistor, this represents a resistor, that's point G, and this is point H. So your task is to uh, determine the direction, alright, of the conventional current. Conventional meaning uh, positive, the direction of the current is from the positive terminal, okay, towards the negative terminal, of course, passing through the other parts of the circuit. We call that the conventional current. We have choices that you have to refer to, all right? So for letter A, is it from B? According to the question, if the terminal B here happens to be positive, remember alternating current, the direction of the current uh, alternates or reverses for every half cycle. There is a reversal, all right, of the current. So the question is considering if the terminal B is positive, what should be the correct direction of the conventional current? Is it letter A from B? Okay, it goes to C, then F, G, H, D, E, A. For B, it's A to E to D to H to G to F to CB, and so on and so forth until option D. Right. What do you think is the best answer? We are going to analyze uh, our circuit diagram. Okay. These 2 wires, by the way, this wire, the horizontal one, and the vertical one, are not physically connected. All right. They are not physically connected. So, uh, what you should do is you're going to trace the conventional current. If point B is considered positive, then we say that the current starts from B. Okay, so what is the next point that current will pass through? All right, just consider the direction of the diode, how it is connected, if it is forward bias or reverse bias. Remember, in a forward bias, we say that current is able to pass through, while in a reverse bias, current is blocked, okay, by the diode. So that is the key concept in answering this question. So, have you figured out what is the correct answer to this question? A, B, C, or D? All right. So let us try to trace the current. If B is positive, then it goes first passing through C. Take note that it will not go that way because uh, it, it's going to, what you call, it cannot pass through this diode because the diode is, as we point out here, this is positive, that's negative. So no way for the conventional current, okay, to go the opposite way. Instead, from point C, it goes here because this is in forward bias. All right. Again, it cannot pass through that diode because it is in reverse bias. Instead, it goes to F, all right, then to G, passing through the resistor, all right, and into point H, all right, and all the way back to point D, and then since this is forward bias, it's able to pass through that diode, all right, And what happens next? All right. After passing this point E, it's now able to pass through, finally, back to terminal A. So, which D, E, A, H, after H, passes through G, then E, and then to A. So, obviously that is letter A. The correct answer must be letter A. For our last question, number 5, it's all about rectification. We mentioned earlier that one practical use of a diode is for rectification. To rectify means a diode, when connected in forward bias, can actually convert an alternating current into a direct current. All right, as shown here, rectification can be demonstrated with a cathode ray oscilloscope or CRO. All right, so this symbol here represents a device known as a cathode ray oscilloscope. All right, the circuit can show the waveform, all right, of an alternating current that passes through it. All right, so in figure 2A, we have here an alternating current coming from a 6-volt power supply. All right, the resistor is also connected across the voltage source and parallel to the CRO. This is for safety purposes. And as earlier described, when we say alternating current, we can imagine the waveform, okay, to look like this, what is shown in this cathode ray oscilloscope. So you will see a sinusoidal waveform. All right. For example, from the rest position of the waveform, all right, when it goes up, it simply means its amplitude increases and then comes back again to zero. So that is uh, during one half cycle. And for the next one half cycle, it goes negative, all right, and back to zero. So the whole wave pattern from this point up, then down, passing through the equilibrium, then to the maximum negative displacement, then back to zero. That constitute what we call a one complete cycle. All right. So positive, then negative, back to positive, and then back to negative. So we have here a two-cycle waveform or wave pattern. That is uh, how the wave that represents the alternating current can be seen in a cathode ray oscilloscope. All right. In figure 2B, there is now a diode. This is the symbol for a diode. The diode now is connected as shown. All right. The arrow indicates that this uh, point here is positive and that is negative. So, in other words, when this is connected in forward bias, meaning if this part of the source is instantaneously positive, all right, we say that this diode instantaneously is connected in forward bias. So current can pass through. All right, but the kind of waveform that is seen in the cathode ray oscilloscope is just half the positive, what you call waveform, because uh, the negative form of the wave has been cut, okay, by the diode. In other words, at an, at an instant when the current reverses in direction, all right, uh, for example, if this becomes negative, then we do not see, okay, the negative part of this wave somewhere here, all right, cannot be seen in the CRO because it has been cut. The current during that half cycle cannot be seen in the CRO because there was no current, in fact. All right. So we call this rectification, the conversion of alternating current into a direct current. We now consider this to be direct current because now the waveform only shows the positive current. The negative current has been eliminated. All right. But you will notice that the current, although it is a direct current, DC, it is not uniform or it is not smooth. The waveform is not smooth. All right. It varies uh, from zero to a maximum, then back to zero. And then there is a moment when there is no waveform that is seen. All right. Then after a while, it again goes up and then goes back to zero. That is the kind of waveform that you can see in the CRO. All right. But when a capacitor amounting to 470 microfarad capacitor is connected this way, all right, what happens is uh, the variable direct current can now be what you call made as uniform or as steady as possible. All right. In other words, during the time when current is not passing through the diode, okay, uh, the capacitor can provide, all right, the needed current that would allow, uh, that would complete, okay, meaning that would smoothen, right? It will smoothen uh, the variable current that is seen earlier in figure 2b. This time, as seen in the CRO, okay, the current, the direct current is more or less uniform or steady current, steady direct current. And that was made possible because of uh, the capacitor, right? The capacitor which stores charges or energy, all right, in its electric field can provide the necessary amount of current needed, all right? Notice that there is a portion here that is of zero current or no current at all. So such current that is missing there during that time can now be provided by the capacitor, all right? And the end result is a more steady current, direct current that is, all right? We call this capacitor a smoothing capacitor. So the role of the diode, which rectifies AC to DC, plus the role of a smoothing capacitor makes the direct current more or less steady, meaning uniform in magnitude and in direction. Only one direction known as direct current. All right? That is what this diagram, the three diagrams show. So your task is to fill up the missing words in the blanks of the following paragraph that pertains to the illustration on rectification shown earlier. Here is the paragraph. All right. When the blank, that's number 1, is placed in the circuit, the current will flow in one direction only. The diode cuts off the negative half of the blank current cycle. This produces pulses of current flowing in blank direction as shown in figure 2b above. This is fine for smoothing or for something like a car battery charger, but not for power supplies for radios and compact discs. Okay, so these devices, radios and compact discs, need a much more steady blank current. Okay, the circuit shown in figure 2c uses a smoothing blank. When the diode conducts, okay, the capacitor blank. When the diode is not blank, charge flows from the capacitor to maintain the current. A blank capacitor gives a better smoothing effect because it can store more charge. Alright? So in answering, alright, or in completing this whole paragraph, okay, there is a need for you to go back and look at the illustration or the diagram. After checking your answers, okay, by referring to the previous diagram, we can now reveal the answers. So the correct terms or words that will complete the whole paragraph, okay, in other words, the words that you are supposed to provide or to write in the blanks, okay, are the following. So the underlined words are the correct words that will make the whole paragraph complete. When the diode is placed in the circuit, the current will flow in one direction only. So the diode cuts off the negative half of the alternating current cycle. This produces pulses of current flowing in one direction, as shown in figure 2b above. This is fine for something like a car battery charger, but not for power supplies for radios and compact discs. These need a much more steady direct current. This circuit shown in figure 2c uses a smoothing capacitor. When the diode conducts, the capacitor charges up. Okay. When the diode is not conducting, charge flows from the capacitor to maintain the current. A larger capacitor gives a better smoothing effect because it can store more charge. Alright, so we are done with this video tutorial. Thank you very much for watching.